Okay, we're looking at properties of buffers here. So a buffer is something that resists the change in pH when either hydroxide or protons are added. They can either be a weak acid or weak base and its conjugate salt. So when they're mixed together, either will resist a pH change to a limit. There's always going to be one to overcome a buffer. The weak component is introduced by having the salt added to the strong of the other. So for example, a couple methods we have here. If I had a weak base, I would like to add some ammonium to that, the ammonium salt, in order to balance that out and actually create a buffer. If I have acetic acid, a weak acid, and I wanted to make a buffer, I would add sodium acetate, let's say. And this would be, of course, the net ionic equation in order to make a balance between these two. Because what this does is it creates hydronium to react with hydroxide, and it creates that the weak acid can react with hydroxide. That it can also react with hydroxide in case that's added in order to balance back. So from here, if we added more acid, it's going to shift it to the left because the conjugate base will react to make more acid. If hydroxide's added, it'll shift it to the right because that hydroxide will react with the acetic acid, making the conjugate base. So we can see that the concentrations change with this, but essentially the pH will have some resistance to that change. Acid-salt pairs. So again, if we have some weak acids, all these weak acids, we can add some salts. Sodium and potassium are often the general go-tos because those will dissociate quite a bit, very soluble in solution. So we can make those concoctions there. Again, anion of the acid and the cation of a strong base, hence the potassium and sodium. Base salt buffering pairs, less common, I'll grant it at that, is because we have to have the weak base, right? These funky ones with nitrogen, and then a salt of those. Again, not too easy to find, but what you want to be clear of is that the anion is of a strong acid, either chloride, nitrate, probably the most common and simple to get your hands on. But again, weird type of things. And again, not as common. You really want to be solid with the acid-salt buffering pairs. So a little calculation involving here. So what's the pH, or I should say what's the hydronium concentration given a solution of a mixture of the salt and the weak acid? So we have, of course, this occurring. We need to have some F present because we start because of the salt, right? This is from the salt that's going to dissociate completely. So we have the Ka, the initial concentration of our weak acid, the initial concentration of the fluoride from the sodium fluoride, giving us solving for our hydronium. Now, the titration of unbuffered solution, you got a weak acid, strong base. We've seen this picture before. A buffered solution, we could see this changes the increase of this here. So let me go back. So unbuffered, goes from 3 to almost 6 before it shoots up. Buffered solution, a little under 5 to 6. So you can see there's a much more gradual change in this buffered region when you already started out in a buffered format. So again, here's another way to compare unbuffered to buffered, because again, they want to look at these. Can you tell if it's even buffered by the titration curve? So again, what way are the graphs different? What are they similar? Equivalence point, same. Endpoint, same. Initial is going to be different, right? The initial pH will be different. And you can see the change of going from the initial to the end to the equivalence point will be much more gradual in a buffered than an unbuffered. All right, so giving you some examples of what these look like. You can always check out AP Classroom for additional stuff. Come in with your questions. Take care.